sent me.
Right.
I'll open it up and grab it. Copy.
Sure.
And
Let me open the same data that I shared with you.
seems to work.
Oh, yeah. Okay. So just copy paste the data in cell C1.
Yep.
Okay. Now, so this is a data set that we have. Now, we want to figure out whether the data distribution is normal or not normal. I mean, basis that we will decide whether we should be looking at mean or we should be looking at median. We'll do the recap in just a bit. Let's get the feeler of Minitab and what it can do. So
Okay.
you just go to stat, basic statistics, and graphical summary.
Basic statistics. Do I have that? Oh, yeah, I do. Graphical summary. Okay.
Okay. So you would see there are two things, variables and bivariables. Ignore bivariables part for now. So just click on the blank portion of variable, or rather there are various ways through which you can bring this data here to variables. One is you can do double click, left click, or what you can do is you can highlight it and then click on select, or you can simply type C1.
Okay.
Okay. So I'll simply type C1 here and then click on OK. Did you get the same chart?
Yep. Looks identical.
All right, perfect. So what we have here, we got the mean, which is 50.56. We have standard deviation, which is 4.56. It has given some figure for skewness, kurtosis. N is total number of data points and information about minimum, first quartile, median, and 95% CI for mean. Okay. If you look here, this value is called p-value. Okay, so as a rule of thumb, whenever we're doing normality test, if p is higher than 0.05, now 0.05 is the value for alpha with 95% confidence. If we run the test with 95% confidence interval, so you see here the confidence level here was 95%. Okay, so because it was 95, the value of alpha would be 5%, so which is 0.05. So if p is higher than 0.05, then the data distribution is normal. If p is lower than 0.05, then the distribution is not normal. So when it is not normal, it means there's presence of too high or too low values which are impacting on the mean. Right, so we should not be looking at mean for this kind of data. Rather, we should be looking at median. Okay, so if you see this bell curve here, there is some data here, right here, right, which is outside the normal pattern or normal behavior of this particular process. Okay, and if you can see in the box plot, there is an outlier as well. And if you bring your cursor there, it will tell you, this particular symbol is for a data which is row number 18 and the data point is equal to 35. Okay, so P higher than 0.05, that means normal distribution. If it is lower than 0.05, that means not normal distribution.
Okay.
Okay. So this is one way of finding out whether the distribution is normal or not normal. There's another way. You go to stat, you go to basic statistics, and you go to normality test. You there?
Normality test. Yep.
Right. So in the variable section, I'll simply select the data. Test for normality, I would keep it at Anderson-Darling test. So Anderson-Darling is the name of the person who developed this normality. So they named it after them. Like that, we have Ryan Joyner and we have Kolmogorov Smirnov. Okay, for now, I will run this test. So the moment I run this, I get this probability plot. Way to interpret would remain exactly the same. You look at the p-value. If it is higher than 0.05, that means data distribution is normal. If it is lower than 0.05, that means it is not normal. Are you getting the same graph?
Yep, exactly.
Okay. Now, if you see there, red dots are the individual data points. And there's this line, blue line going from bottom left to top right. If the data distribution would have been normal, these red dots would be very close, all the dots rather would be very close to this blue line, or rather on the blue line.
Okay.
Visually, you can, by even if you don't go through, all these values, let's say I've removed it, I look at it simply, I can figure out, the distribution is not normal because, there are points which are, pretty far away from this blue line. Okay.
Yep.
All right. So when we do that, we'll be able to find out whether the distribution is normal. If it is normal, we know that a mean is a mean can be used as a measure of central tendency. If it is not normal, then we have a problem. Then we will try to see how we can convert the data to normal, or can we run the non test which is meant for not normal data type. Okay, so this is what is basically covered in this entire slide. There are normality tests like Anderson-Darling, Ryan Joyner, and Kolmogorov-Smirnov, right? And so you need to simply run the data in Minitab, and you would be able to find out whether the distribution is normal or not normal. Okay, so let's see what has happened up till now in the DMAX cycle. What have we done? So we know that Six Sigma is all about project by project approach, right? So you initiate a project by taking the VOC from the customer and convert that VOC into CTQ, prepare the project charter, get the approval from project charter, on that project charter, and then put together the SIPOC. And that is where your defined phase ends, and the output that you get from defined phase that is that you have identified the CDQ which is critical to quality. You have what is your project why, you have your problem statement, goal statement, you have formed the project team, you have freezed on the milestone or the timelines. What are the tools that you would use? You would use VOC to CDQ. You can use quality functional deployment or house of quality. You would use project charter and the SIPOC. Okay, that is in define. Now, what has happened in define? You have defined what is it that you want to do in the project. Then you would enter measure phase. Measure phase is all about three things: what to measure, how to measure, and how to ensure what we are measuring is correct. So what you did is, you initiated with a problem area or a problem statement. You did the process mapping. You mapped the entire process. You try to find out what are the non-valuated steps in the process. What are the waste in the process. and then you did data analysis. Now, before doing data analysis, you wanted to ascertain what is the data type. So, do you remember what are two kinds of data? What are two types of data?
Types of data.
Yep.
Continuous.
Yes.
And what's the other one?
Other one is discrete.
Discrete. I knew it started with a D. I couldn't come up with it. Yes.
Yeah. So
Continuous,
sometimes
discrete.
Continuous and discrete, and discrete data is also sometimes called as attribute data, right? So that's the data which is telling about the attribute of a particular thing, right? So discrete or attribute data. Now, after we have established, what is the data type that we have, we put together a data collection plan to collect the historical data, or if we don't have a historical data available, then we go ahead and collect the fresh data. So after we have collected the data, can we trust the data? We don't know. So we find out how much of a measurement error is there in the data. Are we willing to live with that much amount of measurement error? For that, we do measurement system analysis. So for discrete data set, we do attribute analysis, wherein we calculate effectiveness and efficiency. And for continuous data, we do gauge R&R. So do you remember, Scott, what does R&R stand for?
R&R stands for I want to say recheck and repeat.
Yeah. So one is repeatability and then reproducibility.
Yes.
Right? So that is gauge R&R. And when you do MSA for continuous data, so either there can be error with the equipment. To find out the equipment error, you do test retest, right? And there are two rules. One is you find out the precision, whether your equipment is precise. So if your standard deviation is less than 1/10 of the tolerance, then you would call your system as precise. And then you calculate bias, which is your average minus the true value. Okay, and then you do gauge R&R for operator error. So you do repeatability, and repeatability is same person measuring the same thing with the same equipment. And reproducibility is either you change the operator or you change the equipment. Okay. Then after you've done MSA, and let's say, if MSA fails, then you would not proceed ahead with the project till the time the data is corrected. Okay. So if the data is corrected or the MSA clears, then you would proceed ahead with the project. You would do the baselining. You would calculate the process. So you would calculate the capability levels. So there are various ways it can be done. For continuous data, we have CP, CPK, and PP, PPK is for long term, right? So just like we have Z short term and Z long term, we have CP, which is a short term capability, and PP, which is long term capability. Okay, so there is no difference in the calculation. Calculation is exactly the same, but for long term capability, we generally refer to it as PP. And then you calculate Z score or Z value. Right. So do you remember, ideally in a Six Sigma process, how many standard deviations should you be able to fit between mean and the specification limit and the nearest specification limit?
6.
Absolutely. And between USL upper specification and lower specification limit, how many standard deviations should you be able to fit in a Six Sigma process?
12.
Absolutely. Oh, your concepts are bang on. It's they're clear.
I know
And how that's the main thing. That's what we are studying. So CP. Okay. So let me ask you this. So for a Six Sigma process, what should be the value of CP in an ideal scenario?
2.
2, absolutely. I won't ask any question. I know these are clear. Perfect.
These are easy
And
ones.
let me ask you a tricky one. Okay.
Okay.
CP and CPK, right? So do we know how do we calculate CPK?
With the formula. Do I know the formula? No.
So CPK is with respect to capability on the upper side and capability on the lower side. So CPU and CPL, right? So CPU is calculated as upper specification limit minus mean divided by 3 standard deviation, and CPL is mean minus lower specification divided by 3 standard deviation. Now my question is, and we know how we calculate CP, USL minus LSL by 6 standard deviation, right? So my question is, can there be a scenario wherein CPK is greater than CP?
Can there be a scenario? Yes.
Okay, when can it happen?
When the mean is not in the middle.
Okay, when the mean is not in the middle, then your CP, so the mean would be either towards the upper specification limit side or towards the lower specification limit side, right? So when you calculate CP, CPK is minimum of CPU or CPL. Okay, so let's say if your mean is towards lower specification limit, your CPL would be lower.
If was that one more time?
Okay, so what I'm saying is, let me just show you. So what we're trying to say is, that how we, okay, I'm not able to find it. Let me just open the Excel and show it to you. So how we calculate CP, USL minus LSL divided by 6 standard deviation. Right. This is the formula, right? Okay, now CPK, how it is calculated? So it is minimum of CPU or CPL, right? So CPU is calculated as USL minus mean by 3 standard deviation. Okay, and CPL is calculated as mean minus LSL by 3 standard deviation. So whichever is lower would become CPK. Okay. Right. Now what we are saying is, so between USL and LSL, so let's see if USL, let's say, is 10, mean, and LSL is, let's say, 1, mean is 7, let's say it is 13. Okay, and we have a standard deviation which is again equal to 1. Okay, so this is the scenario, right? So in this, mean is exactly in the middle. So there are 7 points here and 7 points between USL. So if we put it in the formula 13 minus 1, which is going to be 12 by 6 times 1, which is going to be 2, right? Same thing if we calculate with respect to a CPU, which is going to be 13 minus 7, which is 6,
which is 2,
and 3 times 1, which is 2. Okay, the same thing here. It's going to be 7 minus 1, which is going to be 6,
which should be 2.
Right. So in this case, because mean is exactly in the middle. Now what you're saying is mean is not in the center, it has moved. So let me say it has moved and become 10. It is moving towards USL.
Okay.
This is what you were saying, right? So in this case, there would not be any change in this value because it doesn't take into account mean.
Correct.
But this value would change. USL minus mean, which is going to be 3 divided by 3, 1.
Right.
But lower specification limit would become 12 divided by 3. This is going to be 12 divided by 3. Oh, yeah.
That darn formatting.
Oh, yes. You got it now. Sorry. It has become 4. So you see here, CPK is minimum of CPU and CPL. So it is 1.
Okay.
Okay. So there can never be a scenario where your CPK would be greater than CP because CPK is minimum of CPU and CPL.
Okay. Okay.
Okay. Can there
That
be a
makes
scenario where CP is equal to CPK?
Yes, when the mean's in the middle.
Absolutely.
Exactly.
Exactly. We just saw that. Okay.
Right.
So I'll go back to where I was. Okay, so that was regarding CP, CPK. For discrete, you calculate DPU, DPO, and DPMO for discrete data set. Okay, then we looked at, so after we have done the capability, we know what is the current sigma level or current DPMO level of the process, right? And then we will now initiate the analysis. So the first thing that we would want to check whether the data distribution is normal or not. Should I be looking at mean or should I be looking at median, right? So for that, what we did, we checked the data normality using either graphical summary in Minitab or normality test, which is Anderson-Darling normality test, right? And then thereafter, what we need to do is we need to check whether the data is stable or not. So I'll tell you, from where you can check that. And this is what we will do in measure. So after we have done that, the output is the end result of measure is that we know what is the current baseline, and we know the measurement error is not contributing significantly in the data set. So we are okay going ahead in the project. Okay, so we are good with define and measure. Any question in the in these two phases, define and measure?
Not at the moment.
All right, perfect. So let's move ahead and get into analyze phase. Now, before we get into that, let's see, how do we check stability of the data? Again, in Minitab, it is pretty simple. So what you need to do is same data. Let's see if this data is stable or not. You go to quality tools and run chart.
Quality tools, run chart. Okay.
Okay. In single column, just select data. Subgroup size is equal to 1 because there's only one subgroup that we are talking about, and click on OK. It'll plot. Are you getting the same chart, something like this?
Exactly.
Okay. So if you go down here, what you would realize, there are a lot of values which are given. What we are interested in is the p-value for clustering, trend, oscillation, and mixture. These 4 are the special causes in the data, special kind of patterns in the data. If they are present, the data is, or the process is supposed to be not stable or unstable. If P is higher than 0.05, then that particular special cause is not present in the data set. If it is less than 0.05, there is a presence of that particular special cause. So P value for clustering is 0.219, which is greater than 0.05. So clustering is not there. Let's check for trend. It is 0.383, which is again greater than 0.05. So trends are not there. Mixtures, it's 0.781, and oscillation, it's 0.617. Right? So neither mixtures nor oscillation is there in the data set. So that means our process is stable and independent. Okay, this is how you would interpret a run chart. We good with this, Scott?
Mm-hmm.
Okay. So after we've done this, let us enter the analyze phase, and let's see. Now that we know that the project is good to go, and we need to go ahead and start doing the improvement in the project. Now, what we need to, up till now, what we know what the problem is, we have done the baselining and everything. We don't know what is causing that particular problem. So this is something that we will find